So if you look on the right side here, we're going to talk about the confidence level. The confidence level C gives us the overall success rate that the method that we used will capture the true population parameter or the true value that we're trying to estimate. Okay. So if we use the 95% again, 95% of all possible samples, the interval computed from the sample data will capture the true population parameter. So in other words, we used a method that will capture the true population parameter 95% of the time. Am I 100% sure that the true mean lifetime of all batteries produced by this factory are between 15.5 and 18.2 hours? No, we're never going to be 100% sure. So that's what we mean by confidence intervals. I am 95% confident that the true answer lies in here somewhere. So that means 5% of the time I'm going to be wrong. I can't say I'm 100% confident that I know the true answer because I can never test every single battery produced. So a confidence interval, again, has two parts. The interval, which we said down here was from 15.5 to 18.2 hours, and then the level. How confident are we that we actually captured the true population parameter? Oh, in this case, I was 95%. And again, this confidence level can change based off of the problem that we're doing and the seriousness or the importance of what it is that we're trying to find. So if you look down here in the green rimmed box, it's going to give us a sentence frame once again. To interpret a confidence level C, we say if we are to select many random samples from the population and construct a confidence interval using each sample, it's the percent of the intervals that would capture the true population parameter. So if we use the battery example again, I could say that I am 95% confident that the true population parameter, but remember, we need to give it context. So I am 95% confident that the true mean lifetime of all batteries produced by this company in this factory is between 15.5 and 18.2 hours. By talking about the batteries for this company and this factory, I'm giving context to the problem. Very important that we talk about the context. We cannot just say my confidence interval is 15.5 to 18.2. That doesn't mean anything. 15.5 to 18.2, what? About who? So think about that. Who, when, what, why, where, all that good stuff we use. Okay? That all needs to be taken into account when we interpret a confidence interval or a confidence level. Okay? Now, as we talked about before, that every single confidence interval has the same format. It's an estimate plus or minus a margin of error. Now, when you hear margin of error, at least when I heard it for the first time, I thought, whoops, that means that I'm going to mess up. I'm going to screw up. I'm going to make a mistake. I'm going to commit an error. No, that's not what margin of error is referring to in a confidence interval. The margin of error is telling us how wide is our confidence interval? How much leeway are we giving ourselves? And the more confident we are that we captured the true population parameter, the larger the margin of error is going to be. So remember what we said before, that every single confidence interval in the world was estimate plus or minus margin of error. That is the general format, whether it's for categorical or quantitative. It doesn't make any difference. The same form for every single confidence interval in the world. Estimate plus or minus margin of error. The margin of error describes how far at most we expect the estimate to vary. How far away are we from the true answer? We expect our estimate to be, and the last one was like 15.5 to 18.2. Well, that's pretty big. You know, that's over 2.5 hour margin of error, or I'm sorry, about a 1.5 hour margin of error, because the margin of error is plus and minus. It's on both sides of the estimated. So if you look at the examples we have here, you can see that my confidence interval goes from here to here. The center of every single confidence interval is always the estimate. The estimate is smack dab in the middle of every single interval. The margin of error is added and subtracted from that estimate to calculate our entire confidence interval. So every single confidence interval is made the same way. If you look down bottom at this bottom example, this is a 95% confidence interval for the proportion of US adults who are having some sort of financial difficulty. They calculated their p hat, which was 0.65. You can see the estimators right here in the middle, in the center. And then they calculated their margin of error. And we'll look at how we find the margin of error shortly. But right now, they're going to give it to us. The margin of error was about 3.7%. So they are 95% confident that the true proportion of US adults who are having some financial difficulty is between 61.3% and 68.7%. We used a method that would capture the true proportion of all US adults who would be experiencing some sort of financial difficulty 95% of the time. So if we were to do this over and over and over and over and over again, if we were to take an SRS of US adults and create a confidence interval, we did it again with a different sample, we did it again with another SRS, we did it again with another SRS, 95% of all those intervals that we construct would capture the true population's parameter. And that's what this applet is showing us on the right-hand side. Okay? What are we really looking at and trying to do here? Okay? So each black interval, you can see if you look at this first interval, it stretches from here to here. The dot is the point estimate and the width on either side. If the true population parameter mu is this green line running all the way down this picture here, whoops. So if this right here is the true population's parameter, you can see that the majority of our intervals captured it. So what we did here is we took random samples of size n equals 20. We took 25 of those samples, and all but one of them actually captured the true population parameter. Okay? They're going to ask you this weird question. What is the probability that you captured the true population parameter? So what is the probability that our interval captured mu or it captured p? Well, we don't know. The probability is either 0 or 1. We're just not sure which one it is. We are 95% confident that we captured one, but the probability, either the population's parameter mu or p is in the interval or it isn't. So when they ask us this question about the probability of capturing it, we don't know. The answer is either 1 or 0. As you can see, the probability for all these black ones, it's 1, because the true population parameter mu is inside each of these black intervals. The probability that it's inside the red one is 0. The red one did not capture the true population parameter. Okay? So you can see that also listed down here. It's a 95% confidence interval that we constructed. Okay? It captures the true parameter. The probability that it captures the true parameter is either 0 or 1, not 95%. 95% is telling us 95 out of every 100 intervals we constructed this way would capture the true population parameter. Let's take a look at an example here. 2 weeks before the presidential election, a polling organization asked a random sample of registered voters, if the election were held today, would you vote for A or B? Based on the poll, the 95% confidence interval for the population parameter, A, is between 0.48 and 0.54. Okay, so what is this telling us? We are 95% confident that somewhere between 48 and 54% of the entire country would vote for candidate A. Well, how do we know? They didn't ask you, they didn't ask me. How do they know that it's going to be between 48 and 54% would vote for candidate A? Well, they used a confidence interval. Okay? They're not 100% sure. The probability that the true answers between those two values is either 0 or 1. We don't know. We captured it or we didn't, but we don't know if we captured it or not. But we used a method that would capture the true population parameter 95% of the time. So if we did this over and over and over again, 95% of all the intervals would capture the true population parameter. So since this is a question, who would you vote for, candidate A or B, it's not quantitative, it's categorical. Interpret the confidence interval. They're going to ask us to do this over and over and over again. We must provide context when interpreting the interval. So what is the interpretation of this interval? Well, we are 95% confident. 95% confident of what? We're 95% confident that the interval from 0.48 to 0.54 captures the true proportion of all registered voters who would vote for candidate A. Super important that we write context to our answers now. Way different than any of your other math classes before. You used to tell us x equals 10 and your teacher was like, yes, great job. Now you're going to tell me my answer is between 0.48 and 0.54, and I'm going to say, so what? What answer? What does it mean? What does it apply to? What is the context of that answer? Okay, so from 48 to 54 captures the true proportion of voters who will vote for candidate A. We must give context. Okay? So interpret this interval. I am 95% confident that the true proportion of voters who will vote for candidate A is between 48 and 54%. What is the point estimate used to create this interval, and what is the margin of error? Remember, the point estimate always must be right in the middle, smack dab in the middle of every interval. By the definition of the interval, where we take the estimate plus or minus the margin of error, we're adding the same number and subtracting the same number from that point estimate. So the point estimate must always be directly in the middle of the interval. So our interval goes from 0.48 all the way to 0.54. Well, what's the center of 0.48 and 54? Where's the middle of that? Well, we could do that by finding the mean. So if I add those two together, I get 102. I don't like the way that looks. So 48 plus 54 equals 102. The mean of 102 is 51. So my point estimate is 51. That means that this confidence interval has 51 right in the middle. Okay? So 51 is right in the middle. Well, I had to add something and subtract something from 51 to get to 48 and 54. What was I adding to 51 to make it into a 54? Oh, I was adding 3. Does 51 minus 3 equal 48? Yes. So in this case, my margin of error would be 3. So my point estimate would be the middle of the interval, 51. And my margin of error would be 3 percentage points. So I'm 95% confident that the true proportion of all voters in the United States who would vote for candidate A would be between 48% and 54%. My p hat in this problem, my point estimate, was 0.51. Where did I get that from? Finding the middle of the interval. And then question C says, based on this poll, a political reporter claims the majority of registered voters favor candidate A. Use the confidence interval to evaluate this claim. So he says the majority of the voters would vote for candidate A. Majority means more than half. Do we believe this statement is true? Okay. Since the confidence interval goes from 48 to 54, I am 95% confident that the true proportion of voters who would vote for A is between 48 and 54%. I am not confident that it's going to be the majority. I am not confident that it's going to be more than 50%. Okay? Because 50% falls in the interval, then no, I am not convinced that the majority of the voters will vote for A. Just because the estimate was 0.51, we have to take into account the margin of error of this 3 percentage points here. So no, we are not confident that the majority of the voters would vote for candidate A. Now, that margin of error can be very important. If I have a confidence interval with a huge margin of error, then what's the point of making the confidence interval? If I told you that somewhere between 2% and 98% of the people will vote for candidate A, then who cares? Why are we building the interval? So sometimes we want a very small margin of error. We want to decrease the margin of error. And if that's the case, we need to figure out how we can go about doing that. Okay? The smaller the margin of error, then the more reliable or useful the confidence interval would be. Okay? So how can we decrease the margin of error? The margin of error gets smaller when the confidence level decreases. Okay? If I'm less confident, then I'll have a smaller interval, but I'm not as confident that I captured the true population's parameter. Another way to decrease the margin of error is get a larger sample. Well, yeah, the more data I gather, the closer my sample mean or sample proportion will be to my population proportion or my population mean. So the two ways to decrease margin of error, okay, have us be less confident or get more data. In statistics, the whole way through, a good answer is always going to be larger sample size. If you want to make something more accurate or make something better, so to speak, in statistics, always say take a larger sample. It's going to give you a more accurate answer. What the margin of error doesn't account for. So when we talk about margin of error, it's not going to make up for any poor sampling methods. It's not going to make up for any mathematical mistakes or things that you screwed up when you're doing your calculations. The margin of error does not take into account any bias. All the margin of error is doing is looking at the sampling variability. It's just saying, oh, there's a lot of variability in these samples. Okay? So therefore, the margin of error would be larger for the more sampling variability that there was in each one of these samples. So again, every single confidence interval in the world is estimate plus or minus margin of error. Well, what is the margin of error? Where do we get that? Where does it come from? How do we know what the margin of error is? Well, we've looked at the estimate and where that comes from. The estimate's either X bar or P hat. Okay? So the critical value that we're going to refer to here is a multiplier that makes the interval wide enough to have the stated capture rate. Okay. So if I want to be 95% confident that I capture the true population parameter, well, how do I know the width of the interval to be 95%? If I want to be 90%, how do I know what the width of the interval would be to be 95%? Or if I want to be 99%. So this critical value that we're referring to, where does it come from? What are we talking about? Critical value. So what really is the margin of error? The margin of error is made up of a new variable that we haven't talked about yet. So the margin of error is going to be Z star times the standard error. So for now, we'll look at this star as the critical value. This Z star value, or we'll see later we might want to use T star, but for now, let's talk about Z star. And really what it is a Z score. Okay? So if I wanted to be 95% confident, I know that 95% of all data lies within 2 standard deviations of the mean. So if I wanted to be 95% confident, I could think of this multiplier, this critical value, as 2. Because remember, I'm going to do plus and minus the margin of error. The standard error, another way to think about that is the standard deviation. So this critical value, this Z star, this multiplier that we're going to use to construct our interval, where does it come from? And we're going to take a look at where we would get those from. For example, if I wanted to be 99% confident that I capture the true population parameter, let's say I want a confidence interval. Let's start with a simple one. Let's say I want a confidence interval of 95%. Well, if I look back at my favorite picture and I standardize the value, let's say 0, 1, 2, 3, -1, -2, -3. So now I have the standard normal curve. Well, we said before that 95% was roughly 2 standard deviations on either side of the mean. Let's see the exact multiplier or critical value for a 95% confidence interval. And to do this, we're going to have to use table A. So if I want to be 95% confident, that means that 95% of the data is within here. So therefore, 5% is out here in these tells. There's 5% of the data out in the tells. However, that 5% is shared equally within each tell. So therefore, each one of these areas here, these little green areas, would be half of 5% due to the symmetry of the normal curve. So it's 2.5% in both tells, or in each tell, making the total of 5%. Now, if you recall, table A will only give us the area to the left, or the area less than. So I want to know, what is this value right here, this critical value that we would use to construct a 95% confidence interval. So I need, what I'm drawing here in blue, I need to know what area is to the left of that point. Well, that area is 97.5%, or in proportions, 0.975. So I said that backwards. The area is 0.975, which equates to 97.5% of all the data lies less than or to the left of that point. Well, what is that point? Well, let's take a look at table A and see if we can use table A to find that answer. All right, so I need to find 97.5%. So if I look through this table here, where is 97.5? 97.19, 97.26, 97.5. Oh, that's 1.96. So that critical value, that multiplier that I'm looking for, has a z-score of 1.96. So now I know what my critical value is, or my multiplier that I'm going to use for this confidence interval. Well, maybe I won't get table A to go away. There we go. All right, so I know now that this critical value for 95% is 1.96. Well, do you think that's the same critical value for 90%? You think it's the same critical value for 99%? Well, let's take a look here. Let's do another example. Okay. So we said already that for 95%, that the critical value was 1.96. Well, what if I want to do 90%? Well, if we think about our favorite curve once again, 0, 1, 2, 3, -1, -2, -3, 90%. So I want in here, I want 90% of the data. That means that 10% of the data must be shared equally among these tells. So each area here must equal 5%. So this point right here critical value that I would be looking for would be the point on the standard normal curve in which 95% of the data would fall to the left. So again, if I grab table A, I need to find what is that multiplier? What is that critical value that has 95%? Okay, somehow I made this really small, huh? All right, 95% I'm going to find in here. So, 0.945, 0.9505. So it's halfway between 1.64 and 1.65. So it's falling right in this area right here. So it's halfway between 1.64 and 1.65. So at 90%, we would say at 90%, the multiplier or the critical value would be 1.645. And I could repeat this process to be 80% confident, to be 99% confident. I could do this for any confidence level I chose. Now, the 95% comes up so often and so frequently that the formula packet has already done the work for us on the most commonly used. We're going to see a new table. It's called table B that we haven't looked at yet. So what we're looking for here is this new table. It's going to be called table B in your book. And table B is going to be for the t distributions, which we haven't talked about yet, but that's okay because what table B does for us is it finds all of the most common z-score values. Take a look down bottom here. This infinity sign really is z star. So if I want to be 95% confident, I would have to use my z star of 1.96. Yeah, that's what we found when we did the work over here earlier. For 95%, 1.96. If I want to be 90% confident, 1.645. What if I want to be 99% confident? 2.576. So all the most commonly used critical values, the work has already been done for us and put into this table here. So we won't have to do all these calculations that we did earlier if our interval is going to be 90, 95, 96, 98, 99 or 99%, 99.5, and so on. So these critical values or multipliers have all been calculated for us and put nicely into this table. This is a table that you'll have on your AP test and every assignment you do in this class. So you will always have this at your fingertips and you can just look it up. But it's important that we know where it comes from.